In this first example, we're going to look at a monkey dropping from a tree to grab a piece of fruit. And the monkey starts 2.3 meters above the piece of fruit. So here's our monkey, okay? I've beforehand created a nice picture of there's the fruit on the ground, and here's the tree that the monkey's in. And we know that the monkey begins at 2.30 meters. I like to call the ground my y equals 0. Okay, so my initial y is going to be positive 2.3 meters because, like I just said, I like calling the vertical direction positive in these problems. Okay, what else do we know? We know he drops, or it could be a she monkey, but that means, and you have to kind of interpret this, but if something is dropped, that means its initial velocity is equal to 0 meters per second. Okay, so we also know that about the initial condition. So let's go ahead and write that over. I have my setup over here. I'm going to inventory my variables and choose my equation as part of my setup. So let's go ahead, and we know our initial y position is positive 2.30 meters. Okay, we know the final y position is 0 meters. We know the initial y velocity is 0 meters per second. We do not know the final velocity. We do know g, and in this case it's negative 9.80 meters per second squared because we've called the positive direction to be upward, and g always acts towards the Earth's surface. Okay, and finally t, we do not know, but we want to find the time it takes the monkey to reach the ground. Okay, so that's the first thing we're trying to find is t. Okay, let's think about the equations that we know. So we know velocity, the final velocity equals v naught plus gt. This case, we do not know the final velocity. We're trying to solve for t, so there are two things in there that we don't know, so that might not be a good choice for part A. But we also know that the y position equals initial y position plus v naught yt plus 1/2 gt squared. And here we know y, we know y naught, we know the initial velocity, and we know g. So the only thing that's left in that equation is t, so we can solve. We know everything except for one of the variables, and the t is what we're trying to find. So let's go ahead and first kind of rearrange this so it'll be helpful. And we can plug in, we have some values over here that are 0. So if we look, we have our initial y is 0, our initial velocity in the y is 0. So let's think about if this is 0, if this y naught is 0, that gets rid of that whole term, right? The velocity in the y times t, that gets rid of that whole term. And we know our final y is 0 as well. Okay, so then we can write 0 equals 2.3 plus 1/2 negative 9.8 t squared. Okay, so negative 2.3, I subtract 2.3 from both sides, equals negative 4.9 t squared. Okay, you can see where this is going. We divide both sides by 4.9, and we get, I didn't write down my work enough to know. I could plug it in the calculator, but I'm too lazy to do that again. I do know, however, what the square root of that is. That's going to be either plus or minus, so I'm going to choose the plus because we wanted the time. This is going to be positive time as he's dropping. We're starting time equals 0 up here. Okay, we don't want to look back in time, we want to look as he drops. So we're going to choose the positive 0.685 seconds. Okay. So now that we have a time, we can take our time and actually solve for what we're trying to find in B, which is how fast is the monkey moving just before it reaches the ground. Okay, so we're going to take this that we found right here, this time, and we're going to take it and we're going to plug it into that equation. And then we'll know everything except for that final velocity. Okay. So let's write down our equation. Okay, so now this is for part B. We have velocity in the y, which is what we're trying to solve for, equals, well, our v naught was 0 plus negative 9.8. I'm going to run out of room here. Times, we're going to go downhill here, 0.685. And I carried out the decimal places, so I think it was like 0.68512 or something like that when I plugged it into my calculator. I just actually took my answer from the previous part and multiplied by negative 9.8. Okay, so that means our velocity when the monkey reaches the ground. Okay, and you'll notice that we plugged in that exact time when he hits the ground. So we're plugging in that time and saying that like the instant he's hitting the ground, his velocity, correct? He's going to decelerate really quickly and have a positive acceleration that'll slow him down and he'll stop when he hits the ground. But we're talking about just that split second where he's like just about to make contact with the ground. Okay, and that is what we solve for the time. So we plug that in and we get a velocity of negative 6.71 meters per second. So here's our next example. We kind of have a biology theme today, I guess. So we have a springbok type of deer thing. And when it's startled, it leaps up several times in succession, and it can jump up to several meters in height. So this is called pronking, and during one such jump, this springbok here leaves the ground at 6.0 meters per second squared. Okay, so let's say here is our reference frame. This is where we'll call this x equal, or sorry, we're in the y direction, right? So y naught equals 0 meters here. He started on the ground and he left the ground with a initial velocity in the y direction of 6.00 meters per second. Okay, so we can fill in that information into our setup over here with our variable inventory. V naught y, 6.00 meters per second. Okay, and we're trying to find what maximum height above the ground does this springbok get. Okay, so he jumps up. Remember, we're modeling his center mass, and then he comes back down. So we want to know how high he gets. So we want to know y at the height of his jump. So to do a little bit of thinking here, what other piece of information do we know if he's at the highest point in his jump? Well, we know from just like looking at objects that are thrown up in the air, just straight up in the air, they come to us like a stop momentarily and start coming down. So that y velocity at the top of his jump, okay, this velocity in the y direction is going to be equal to 0 meters per second when he reaches the highest point in his jump. And this is a key piece of information when you're dealing with these free fall problems, that if you're trying to find the highest point in the toss, in the jump, whatever you're looking at, when it reaches its highest point, its velocity in the y direction is 0. It no longer has a y velocity. It's that split second where its velocity is going from being positive to being negative. Okay, for a split second there, it's 0 meters per second. Okay, so that's an additional piece of information we can put in here. We do know the final velocity there. Okay, we don't know anything about the time. Why, we don't know, but in part 1 here, that's actually what we're trying to find. Okay, we want to find what is that point, that displacement, or that highest y position that is reached by the springbok during its jump. So let's think about the equations we know. Well, we know velocity in the y equals v naught plus at. Okay, we got an issue there though, because we're not trying to find t, and that's the only thing we don't know in that equation. Okay, so not super useful right now. we also know y equals y naught plus v naught yt plus 1/2, my t's, I need to put the little curly q at the bottom, 1/2 gt squared. That differentiates it from my plus signs. Okay, with that one, again, we don't know t and we don't know y, so that one looks almost even worse because we don't know both of those things. But let's take a look, and what tips you off, if you don't know time, a lot of times the best, a good equation to start with would be by squared equals v naught y squared plus 2gy minus y naught. Okay, because when we look at that one, we're trying to find y, okay, and we know initial, final, and g. Okay, oh, and we know y naught. We're setting that equal to 0 because of that. We conveniently set up our reference frame so that y naught was 0. Okay, so our setup is complete. For A, we've chosen that this equation is the best one to start with. So let's figure out what maximum height does the springbok attain. And then we can go back, how long does it take to reach its height? This first equation looks like probably a good one to use. What's its velocity when it's 1.25 meters above the ground? We could probably go back and use so we're looking at its height or its velocity when it's, so this one would be good again. Okay, so we'll use this one for A and C. Okay, this one looks like the best choice for, you know what I'm meaning, 1 and 3. This one looks the best choice for part 2. And then the last one, at what times is the springbok 1.25 meters above the ground? Okay, so that one might be, this might be a time where we want to use this one. Okay, so tentatively that's our plan, and let's check out what we need to do for 1 to plug in our numbers and solve. Okay, so going ahead and solving for part 1, we can plug in our numbers. We know, let me scroll down a little bit so we can see that. So our y velocity at the top is going to be 0. 0 squared is still 0. 6 squared plus 2 times negative 9.8 times y minus 0. Okay, that simplifies down very nicely. We can square 6 and move it to the other side. We get negative 36 equals 2 times negative 9.8 is just negative 19.6. And then y minus 0 is just y. So we can just divide 36 by 19.6 to get our value of 1.84 meters, which is like above my head. So that's cool. That little deer can jump quite high. Okay, moving on to the next part. We said, so next part, how long does it take the springbok to attain this height? Okay, so now we got to plug our numbers into this first equation we wrote down up here. So, and we're just going to plug in that time and the other things we know. So let's write it down here. Vy equals v naught y plus gt. Well, we know Vy is 0, 6, okay, so we subtract 6 for both sides, and we get 6 divided by 9.8 equals t, which is going to be 0.612 seconds. It's got some hang time there. Okay, so that was how long does it take the springbok to attain this height. Okay, so 1.84 meters, and it takes him 0.612 seconds. Okay. Next thing I ask you is, what is the springbok's velocity when it is 1.25 meters above the ground? Okay, so here we know we know the height and we know the initial height. And when this springbok is above the ground, so let's think about, so he's jumping up and then coming back down. So he's going to pass through 1.25 meters 2 times, right? So that makes sense, because if we were to plot his y position versus time, it's a parabola and it would cross that 1.25 meter mark 2 times. So we're going to solve for this and we're going to get 2 answers, which is what we want because he passes through the 1.25 meters twice. Okay, so let's take a look. Again, we're going to want to use b squared plus 2g is y naught. Okay, and we know now y is 1.25. Our initial position is still 0, so 1.25 we can plug in. 2 times 9.8. Okay, we know our initial velocity was 6, and we're trying to solve for that y velocity. So this we don't know, but our equation is conveniently set up so that it just, we will solve for it. Well, we'll solve for the square of it. So that equals 36 plus, what is that, 19 or 18 point. 19.6 times 1.25, and we get 11.5. Oh, because this is negative. Y'all, I forgot my negative sign. Squeeze that in there. Let's keep that negative sign. I'm doing this for years and I still miss the negative sign sometimes. Okay, so that equals 11.5, and that's equal to velocity squared. So in order to find that velocity, it's the square root 11.5. So we get positive 3.39 meters per second and negative 3.39 meters per second. Okay, for that answer. And that makes a lot of sense because going this direction, the y velocity was, the slope is positive, right? Going up, okay, and this side, slope is negative, it's going down, okay? So the velocity is positive, velocity is negative. Makes sense. And there's symmetry in this graph, so that's very nice. We know that it's going to be, if we're at 1.25, if we have a positive velocity of 3.39, then when it passes through, when the springbok passes back through 1.25 on the way down, it's going to have a velocity of negative 3.39. Okay, ooh, we're getting way down here. I got to scroll back up. Okay, last question. At what times is the springbok 1.25 meters above the ground? Okay, so for this last one in part 4, we just solved for the velocity. So I've actually adjusted my thinking from when I started, which is fine. You can do that because I didn't realize we were going to be solving for that velocity. So now we know velocity, initial velocity, and g. So we can solve for time. And this is a simpler equation. This sometimes I end up with a quadratic, which is not super fun. So if I'm able to use this one, then I want to choose that one. So for part 4, I'm again going to use that equation, and let's just plug in those velocities. We got to scroll way down. So this is part 4 now. So we have 3.39, right? We'll start with the positive one, equals 6 plus negative 9.8 times t. Okay, I could have rearranged this, and I should have maybe rearranged this before I plug stuff in. So Vy equals V naught y plus GT. If I subtract V naught y from both sides and divide by G, that'll give me T. Okay, so that's what I'm doing over here, 3.39 minus 6 divided by negative 9.8. That's going to give me a t of 0.266 seconds. Cool. Okay. And then I'm going to plug in negative 3.39 and do the same thing to give me t. And that's going to give me 0.958 seconds. Okay. So I take a look at these answers. I would expect that, oh, there we go. You can just make it small. I would expect that this would be before the time that I solved for here, right? And it is, yay, okay? And this time to be after, okay, double yay. So that makes sense. We talked about the symmetry in the graph, so that made sense. This was 3.39 was less than 6, so that's another check. That initial y velocity was 6 meters per second, so definitely would need to have at 1.25 meters, it would be less than 6, and it was 3.39. So that's good. And let's see what else, if we can make sense of our first one. This also seems reasonable. It's not, I mean, that's kind of a high jump, but it's not like it's 10 meters. Okay, so that seems like a reasonable number as well. So there are your two examples using wildlife of our kinematic equations for free fall.